Hello guys, this is Kimitsu, and today I'll try to explain UminekoRox's CLE, carry look everywhere error concept. I had to reverse engineer it from his video. Okay, so for any of you who needn't actually watch the original video, all he does is basically drool over his 9-tick LU, which is, to be honest, not too fast. I mean, even for pistonless ALU. So, up to the point where he gets to his adder part, which was his CLE concept, and he wants to explain it, but he doesn't want to explain it. He just laughs in our face. Okay, so I needed an adder at this point. I'm trying to build something with redstone, and I was looking for various adder concepts, and I basically liked how it looked in the video, but I didn't have a clue how to build it or how it works. So, but thanks to the fact that Mineko was running around his contraption several times, I got some still frames and was able to recreate part of it. And then I had to figure out how it works, and now I got this. So this is input bits for the adder, this is the other operand, this is carry in, those are output bits 0, 1, 2, 3 and carry out. So it adds pretty fast, I guess, for pistonless adder. So note that the original adder was 8-bit. I got only 4 bits just for simplicity. It basically is extendable pretty easily. So yeah, it adds, just trust me, it does. The question is, how does it work, and why is it so fast, I guess? Because normally you'd see a bunch of really weird gates in adders, especially if they don't use pistons. There's just no obvious way to carry to propagate carry. So in this adder it looks really empty inside, somewhat. So one would wonder, how does that work? And that's what I was able to figure out, and I will try to explain it. So here we have a core of the adder, let's say so. It is stripped of its input gates. So all the logic behind the adding itself is somewhere around here, while gates are simply XNOR and stuff like that. So let's start from the output. Every bit in the output line is connected to the XNOR gate. So this gate has 2 inputs, from the above and from below, and it will only turn on when the inputs are the same. So this XNOR gate, and this is the top side of the wiring. Surprisingly enough, it's very simple. It's just bus turning 90 degrees and running straight into these XNOR gates. So nothing branches off this bus and nothing really happens to it. So it's easy. The next part is a bit more complicated, I guess, but it is pretty easy too. So, but before I will be able to explain it, let's actually see what happens here. Here we have our inputs. Remember that we stripped input gates off, and that was actually how I got this. So I was able to get this part from the video, but I didn't have a clue what kind of input does it take. So let's just say that I figured out that this was not carry in. So when we turn this off, this means that we want to put carry side of the machine, and this is the output on the first bit. Now here we have our key parts of this CLE concept, which are these glowstone encrusted lines. They're like triangular shape all the way here, one less here, and only one here, and there's nothing of sort on the last line. So these lines are basically where the carry signal propagates through the bits, and as you can see, the signal travels one way but not the other. So when we turn the carry off on this side, it did depower this block, and there's a torch underneath. So this torch powered the lower output wire, and the lower output wire is feeding into XNOR gate. XNOR gate powers on, and we have our output. But why doesn't the signal go further? Well, this is because this OR gate over here, right over this glowstone block, there's an OR gate, and the input into this OR gate is here. So if we look at these lines here, they all have OR gates above glowstone or above blue wool blocks. This happens because they need to be alternated left and right, so they won't actually feed into each other. So the input for these OR gates is basically the same as on the top bus. So it splits over here, then it turns here and feeds into each OR gate individually. This is pretty simply designed. It's really neat. So what this effectively means is this OR gate stops the propagation of the carry. So if we want the carry to propagate, we need to depower this input over here, and we see that carry signal got further, depowered this block and activated this torch. So this torch powered this XNOR and the output is on, but at the same time the top bus got depowered and our previously enabled output on the 0 bit got turned off. So very interesting, we can depower this and the carry propagates even further, and this, it goes further and all the way to the last bit. Let's say we actually power this thing again. See? What happened is carry stopped propagating at this point again. All of the torches there underneath the glowstone bits got turned off again, and since those inputs are depowered, the 3 outputs there got powered again. So what this means actually is these inputs are propagate flags, let's say so. So if you ever heard of Cogstone, or whatever it's pronounced, adder concept for the parallel calculation, it has P and G values that actually get changed on each iteration of the algorithm. So the output, so the formula, like the logical formula for this adder, sort of looks like Cogstone, but it's not exactly the same. So, and this line is obviously, since this is the carry, and this must be the carry carry that generates on in the process of the sum. So let's turn all of this back and say we have this propagate. So what does this mean? This actually means that there is one O or O1 sum at this bit. So this line is basically stripped of the order of the operands. It's just XNOR of them, basically. So if we turn it on, it might mean that there are 2 zeros or maybe 2 ones. And to actually inform the core of what it is exactly, we have this an AND, not AND gate, not AND input. So basically it means that when we power this off, it generates carry along this line. And here we go. It goes to the next output bit, and we can propagate it further. So yeah, this is how it works, basically. So based on what we've seen, we already know that we need an XNOR gate here and somehow feed not AND to these lines. And this is what those gates are for. They basically do exactly that. Very interesting concept, but why does it work? Well, honestly, to completely be sure that it works, you have to just write the formula for each of these inputs, for each of these outputs, like how exactly they got calculated with the logic we have here. And in the result, we actually will get a full-scale addition formula, but it's kinda the only way to be exactly sure that it always works and does not make any mistake. Yeah, but the basic concept and well, how you can explain it like easily is just, you can't propagate carry over one bit twice. So in basic addition of two numbers, each bit can propagate only one carry. So you will never need another bit to be propagated from when you're adding two numbers together. This is a little bit of my idea of how to be sure that this works. But So this design is basically an instant carry. It uses the fact that these repeaters, one-way repeaters, are actually timeless, tickless, or something, zero tick. The only parts it loses ticks are those input gates, output gates, these OR gates, but basically it's just 2 ticks here, OR gate 1 tick, 2 ticks here, and there's actually this, so 1 more tick. So it's actually about 6 ticks. Well, this thing here, yeah, it adds to it, probably. Not really, because it gets to the XNOR gate before the bottom line actually gets fed into it with proper values. So yeah, 6 ticks. Let's go ahead and okay, what was it? Yeah, the question was about, in the video UminekoRox's mentioned that the output is 3 wide and that it's not that much of a problem, to be honest. Well, to be honest, it's not, but you would actually lose some additional time with repeaters to tighten the output bus up. So in order to deal with, and also these repeaters over here, they add the delay, so the longer your adder is, the more bits it has, the more repeaters in the adder you will need to place, and making it smaller, or rather thinner, on the output side will actually contribute to the speed, probably. I'm not entirely sure, but let's see what problems are there when we try to actually make this smaller. So the first thing that comes into mind is this thing. You can't just place this glowstone to the left and lower this blue wool block, because the redstone signal won't go down from the glowstone. So this is problem number 1. Problem number 2 is those repeaters. They have to alternate like this, otherwise they will feed into each other and or will not be instant. So you can apply input here, yeah, and it will go to that repeater, but that's not a good thing, because currently it's just one input goes into all of the 3 repeaters, so it's only 1 tick, right? So let's just try and do something about all this stuff. So what we have here is what I got. So yeah, it's an error. It does pretty much the same. I bet it's about 6 ticks too. I speak about because I don't know much about redstone computing, and I'm still new to this, so I'm not sure if I can calculate it right. So let's see. First problem is easily solved, straightforward, just make it go up all the way. Pretty simple, huh? Pretty simple. The second problem, even more easy. Just get rid of those repeaters. You can't place them like that. Get rid of those repeaters and put a bunch of torches, which would require actually our top bus to be inverted. And this leads us to XOR gates instead of XNOR gates at the input and at the output. So I had to change the gates here and here, and it all became, actually, I like this. It's a little bit more clear in my opinion, and it's definitely too wide output. So let's actually see how it works. So let's put 1 in our input number 1. So what we see here is propagate line got turned on. That means that this bit can propagate carry. So if we actually turn the carry on, input carry, we will see that this torch is depowered and the carry goes on. Let's turn this on. Off. So let's turn on the first bit of the B operand. Now XOR gate turned off this thing and turned off this thing, which is not AND. It's the same basically. So it doesn't propagate carry anymore, but it generates carry. And that's what we see there. So when we turn this on, it propagates carry, the second bit. When we turn this on, it stops propagating carry, and this is correct. And it generates carry. And this carry can get propagated even further and further. So that's how it works intuitively, right? To completely understand the logic, you will have to write the formula and stuff like this, but this is not the point of the video. This is just to get you a good look on this technology, instant carry, or carry look everywhere. Sorry. So really good clean look, and actually I will post a URL to download in the description. So yeah, I hope you enjoyed it. Thank you for watching.